Hello and welcome to the ninth lecture in our BQIT series. Today we'll be talking about open quantum systems, which are basically quantum systems that interact with the surrounding environment. Now, up to this point, we've been only dealing with closed quantum systems, which are quantum systems that are isolated and therefore undergo unitary evolution according to the Schrödinger equation. Well, in this case, we have to include the effects of environmental interaction, which means that the evolution of our quantum system may not always be unitary. So the first topic we'll cover is called our quantum measurements. Now, if you recall from the second lecture, every single measurable physical quantity in quantum mechanics is described by a Hermitian operator A, which acts in the state space H. And this operator is an observable. Now, the result of measuring such a physical quantity must be one of the eigenvalues of this observable. Now, when the physical quantity is measured on a system in a normalized state psi, the probability of obtaining an eigenvalue of the corresponding observable A is given by the amplitude squared of the appropriate wave function, or the projection onto the corresponding eigenvector of that A. And so, when this measurement occurs of the physical quantity A, we can measure, we can, well, the state psi collapses into one of these eigenstates, which can be modeled by the application of a measurement operator associated with a certain measurement outcome to the eigenstate psi. So what are measurement operators? Well, quantum measurements are described by a collection of measurement operators, and these are operators that act on the state space of the system being measured. So for each measurement operator, there will be an measurement outcome M, and for each outcome, we can associate a probability Pm, the probability that result M occurs. Now, when that result M occurs, the state after the measurement will change from psi to the application of measurement operator MM to that psi. And the expression you see in the denominator is a normalization factor, which is there to keep the norm of the final state to 1. And of course, since the sum of all the probabilities must be equal to 1, the measurement operators need to satisfy this equation called the completeness equation, which basically is there to ensure that the sum of the total probabilities defined above is equal to 1. Now, let's say, for example, we are measuring a qubit in the following computational basis, M0 and M1. Then the measurement operators can be defined as the projectors onto these two states. Let's say we have let's also say we have a psi, a 1-qubit psi, in the general case, so it's defined as the following. Well, we can see that our operators, of course, they satisfy the completeness equation trivially. As you can see, they add up to the identity operator as we want. And through the definitions above, we can also see that the probabilities of measuring 0 and 1 are equal to the respective probabilities we would expect from the Born rule. And so that when we apply our operators with a normalization constant, we mostly get what we would expect after measuring each of the basis states 0 or 1, except for a global phase. Now, there are two different measurements we can define using such measurement operators. The first is called projective measurements, which is basically most measurements in quantum mechanics are basically projective measurements. So this is an important special case of the general measurement framework we've defined above. And most projective measurements, together with unitary dynamics, are sufficient to implement general measurements. So most of the time, what you'll need is basically a projective measurement. And by that, I mean that we can define a unitary operator with psi and an ancilla to store the final measurement state. And then this can be used to represent the final result of a measurement on psi. Now, a projective measurement is described by an observable M, and the observable has a spectral decomposition by definition, since it is Hermitian. And M can be represented as the weighted sum of the projectors Pm onto the eigenspace of M with an eigenvalue M. And of course, we can use the definitions above to define a Pm, a probability that the result M occurs. So this would just be the expectation value of the projector Pm. And in this case, the state after the measurement, of course, would be the application of the measurement operator, which is in this case Pm. And you can see that the expression here is simply Pn due to the definition of a projector. Well, not really definition, but the relation that all projectors must satisfy over here. And apart from your everyday projector measurements, there's also what's called a POVM measurement, or positive operator valued measurement. So in most cases in measurement statistics, of course, we have a associated probability and an associated post-measurement state. And POVM measurements are basically a more general form of the projective measurement framework we've defined above. So for positive operator value measures, let's say we have this common operator, this M of M dagger by F of M, and this is used to calculate the measurement statistics or the probability. Well, let's say we can just define any positive operator to be equal to this, and we can easily see that would always be positive. So how about we take the reverse approach and we define a positive operator to be this value. Of course, by the completeness equation, needs to satisfy completeness, the sum of each positive operator will be equal to the identity. If this is the case, then of course the probability of an outcome M would just be the expectation value of this positive operator. So in general, the measurement outcomes can be represented by a set of different positive operators. And this is a more general framework than the projective measurement above, which required that E of M be a projector. The reason we use POV measurements is that sometimes, unlike in projective measurements, our measurement is destructive, such that we can only measure our state once instead of projecting our state many different times to reconstruct our probability. So in order to encompass this case, we generalize our framework to the POVM measurement formalism. So the next topic will be on density operators. So density operators are a more general way of representing quantum states. So the quantum states we've seen here so far are represented by a bra or a ket vector here, but these are only really suitable for representing what's called pure states. If you want to represent something more general, which is called mixed states, we need to use what's called a density operator. So before we get into what a density operator actually is, what pure mixed states are, let's cover some preliminary math, such as the trace and the concept of a positive operator. So the trace of a n by n square matrix A is defined as the sum of its diagonal elements over here. And then this trace operator has a few different unique properties, well, useful properties that we can use in various different proofs, such that it is additive. That is that we can add the traces to get the trace of the sum of matrices. It also satisfies the property where we can simply multiply a constant by the trace value to get the trace of a constant multiplied matrix, i.e. 1 and 2 mean that the trace operator is linear. And for this trace operator is also commutative for matrix product, which is property number 3. The trace between the tensor product of two matrices can also be easily calculated by simply taking the product of the traces of each of the matrices being tensor product. So, in addition, another useful way representing the trace is like so, in which we take the expectation value of each of the basis vectors for our matrix or operator A to calculate the trace. And this, as you can see, is just equivalent to taking the diagonal sum of the diagonal entries in the matrix A. So next, a positive operator or a positive semi-operator is represented as a operator in which the eigenvalues in which the expectation values are always greater or equal to 0 for any arbitrary vector in state space. And according to this definition, a positive operator is necessarily Hermitian, which means that its eigenvalues are necessarily real. So to prove this, we can just set A, suppose A is an operator, and we can write A as the sum of these two expressions. So the first expression is a Hermitian operator. The second expression is what's called an anti-Hermitian operator. So we can always split up a operator into two parts, B that is Hermitian and C, IC, which is anti-Hermitian, which makes C Hermitian. And since B and C are Hermitian, it means that necessarily if A, the expectation value of A is always greater or equal to 0, then A must be Hermitian. That means C must be 0. So let's say that A is a positive operator, and suppose X is an arbitrary vector in state space. So let's take the expectation value of A with respect to this vector. Plugging this in, you notice two expressions here and here, and this must be greater or equal to 0, but these values must be real because we've seen that B and C are Hermitian, respectively. And since these must be positive or equal to 0, we'll see that C must necessarily be equal to 0 since X is an arbitrary vector, which means that A equals to B. And so, supposing that A is a positive operator, we can write A as the following spectral decomposition because we've always seen that A is a Hermitian operator. Now we've gone over some of the preliminaries. Let's also cover what an open quantum system is. So recall the second lecture, which state that the evolution of a closed quantum system is described by a unitary operator. Well, the density operator provides a convenient means for describing quantum systems whose state is not completely known. So, for example, in the closed quantum systems case, we knew exactly what each of the entries of our bracket vector is. But sometimes we don't have all of the information required to define such a vector, which is where the density operator framework comes in. So a common situation in which such states occur is in which we have a system of two qubits which are entangled each other, but the environment interacts with one of them, which causes one to collapse. But this means that we don't actually know the measurement result of qubit B, which means it's not certain what state qubit B is, and also that makes it uncertain what state qubit A is, since they're entangled. Now, In this case, we can represent the situation as an ensemble of different possible quantum states, depending on each scenario. So if a quantum state is in a number of states, psi I, where I is an index with respective probabilities pi, you can define what's called an ensemble of pure states, which is basically a set of each of the possible different states and the probabilities according to different scenarios. And we call this ensemble a mixed state. So for example, let's say A and B are entangled, and if B was supposedly collapsed into the zero state, A remains in the zero state. And if B collapses into the one state, A remains in the one state. So for our mixed state here, P1 can be defined as 0.5, psi1 equals 0, P2 equals 0.5, and psi2 equals 1, which means that we can define the state of qubit A to be in this mixed ensemble of state, or this mixed state, since we're uncertain about the measurement outcome of B. So in order to represent this more clearly or in more coherent fashion, we're going to define something that's called a density operator or a density matrix. So let's take our ensemble and simply define different projectors of each of the states here, and then weight them by the probability here to get what's called a density operator. So when our density operator goes over a unitary evolution, since each state that goes under a unitary evolution according to U gets transformed into U of psi, we can define rho as this as follows, and each individual state would be unitarily evolved into this state, giving us this expression for defining a unitary evolution of rho, which is also termed as what's called a conjugation operation. In addition, the probability of measuring our mixed state into the state outcome M is defined as the following, with M dagger M rho being traced over to get the probability of measuring M. So we can prove this as the following. Suppose that our state is an I, which means that the probability of measuring our state to be an M is defined as the following according to measurement operators. And then this can be rewritten into this form as a trace. Now, to get the total probability, we just need to multiply this conditional probability by the probability of the state being in psi I in the first place, getting this expression over here. And then since the trace is linear, we end up with this final expression over here. Now, after measurement, the density operator is conjugated according to this density operator to get rho m, the mixed state of the system, after obtaining a measurement result m. So let's suppose for each psi of I, to prove this, let's suppose after each psi of I, we measure it and we get a result m. So according to measurement operators, it will be projected into this state over here, and we're going to define this as psi of I and m. So after measurement which yields the result of m, we have this following U ensemble, which defines a new mixed state rho of m, and we can write this as so. And according to their definitions, we can write this as this expression. And by using Bayes' law, we can extract the probability of state being I given a measurement outcome of m through these other probabilities quantities we know of. So afterwards, we can just go through all this algebra. These two expressions cancel out, and we get a pi at the front. And then we can rewrite this into this expression, which we saw over here. So our density operator, we know how our density operator evolves under a unitary and how it changes under a certain measurement. Now, what properties does the density operator satisfy? Well, first, the expectation value can also be represented using the density operator formalism. So we take the same approach of proving everything by just superimposing the different measurement outcomes and weighting them, the different expectation value outcomes and weighting them by P of I, and rewriting everything, we get this final expression for the expectation value according to I, A. And the density operators, such density operators also satisfy a few useful properties which can be manipulated in certain proofs. The first is the trace condition, in which that states that the trace of rho is always equal to the one. And this comes from the normalization condition of the probabilities, that the sum of each of the different outcomes of the different states they can be in needs to be equal to one. And so we can prove this as just writing the definition of rho, taking the trace of both sides, taking the trace inside because of the linear property, noticing that this is an orthonormal state, and so we get one. Another useful property of density operators is that the density operator is always a positive operator, positive semi-definite operator. This can be easily be seen by taking the expectation value of rho according to a arbitrary vector, and then noticing this expression becomes positive, which means that since pi of I is a number between 0 and 1, this expression will always be positive or equal to 0, in the case of psi being, of course, orthogonal to each of these possible states psi of I. So, using this formalism, we can define what a pure state is and what a mixed state is formally. So a pure state can be defined as a quantum system whose state psi is known exactly. And in this case, the density operator can simply be written as this projector operator of the state that is known, psi. But in the case of a mixed state, it's a mixture of different pure states in an ensemble. So given this definition, we can use this following criterion to decide if a state is mixed or if a state is pure. If we take the square of the density operator and take its trace, if we get 1, then the state is to be defined as a pure state. Otherwise, if this value is less than 1, it's defined as a mixed state. So in case 1, of course, we can prove this in case 1. If it's a pure state, then of course we could represent it as so. And then taking the square, we just get rho as before. And as we saw above, the trace of rho is always 1. So the trace of r squared will be 1. But however, in the case of a mixed state, we can represent this as so. And then taking the trace of r rho squared can be represented as this expression. And we take the trace of this. And since the trace has a linear property, of course, we can rewrite this to be the weighted sum of this expression. And the trace of this can be rewritten to be the expectation value of rho of I, which is, of course, always less than 1, which means that we are left with this on the right side of the inequality, which we know is equal to 1. So we always know that the trace of rho squared is always less than 1. Okay. So let's move on to the decomposition of the density operator. So let's say we have the following density operator over here. So a simple diagonal operator. We can rewrite this as the weighted sum of these two matrices, which can also be rewritten into the projections of these two vectors, which means we can rewrite this as this expression over here. Now, you notice that this means that this density operator represents the ensemble of the state being in the 0 state with a probability of 3/4 and the state being in the 1 state with a probability of 1/4. Now, suppose we define these two different states A and B. If you do the algebra, you notice that rho is equal to this ensemble instead as well, in which this state has a equal probability of being A or B. So what gives? What is the correct ensemble? So it turns out two different ensembles of quantum states can give rise to a specific density matrix. So in general, eigenvectors and the eigenvalues of a density matrix just indicate one of the many possible ensembles. That is, there is no one ensemble that definitely represents a single density operator. Or the other way around, one density operator corresponds to many different possible ensembles. So that's just one caveat to keep in mind when working with density operators or density matrices. So we saw earlier in the second lecture or the third lecture about the Bloch sphere for pure states. Now we can also talk about the Bloch sphere for mixed states as well. So given a rho for a mixed state qubit, which is a 2 by 2 matrix, we could represent it as this form, where R is a real three-dimensional vector with a size equal or less to 1. And this sigma expression is simply a vector expression which is comprised of the Pauli matrices. And so the inner product of R and psi, no, not psi, sigma, is defined as simply this weighted sum over here with R1, R2, R3 instead. So this can be done. We can write our rho as this because the Pauli matrices, along with the identity matrix, they form a basis of the 2 by 2 matrix space, which basically means that every single 2 by 2 matrix can be represented by a weighted sum of these four matrices. And so the density operator is no exception to this. So since rho is a Hermitian operator, we can write rho as rho equals this weighted sum, of course, as I mentioned earlier, where these are real numbers, of course. And let's say we take the trace of rho. On the left-hand side, we know this trace is 1. And so by the linear property, we can also take traces of these, but for each of the Pauli matrices, this trace is equal to 0. And so we're just left with 2 of mu 0 being equal to 1, and mu 0 equals to 1 over 2. And so we can also take the square of the density matrix, and doing all the algebra over here, we get this expression over here. And using the commutation relations of each of the Pauli matrices, of their product relations. And so doing some more algebra, we get this final expression, and we can take the trace of both sides to get this final expression on the right-hand side, since these are all 0. And then what happens is that we know that this value must be less or equal to 1, and so we get this following inequality. And so this vector v, or nu, has a size that's less or equal to a half. And if we just define r to be 2 times that, we get the size of r is less or equal to 1. And so we can write this form in terms of the r vector instead of the v vector to get this final expression. And so according to this definition, we can define a Bloch sphere for mixed states with the Bloch vector being the vector r. And according to this interpretation, we get the result that rho is pure if and only if this Bloch vector has a size of 1. Or in other terms, that the Bloch vector is on the surface of the Bloch sphere. And this is easily proved by using the condition that rho is pure if and only if the trace of the square of rho is equal to 1. And so for the Bloch sphere on the pure state, just to recap, we can represent each state as this expression in terms of these two parameters, the angle theta and phi, which will correspond to the two angles theta and phi on the Bloch sphere shown in the figure on the left. And so we can use this framework, of course, to show that the Bloch sphere for mixed states encompasses the Bloch sphere for pure states by calculating the density matrix for the pure state psi in such a fashion over here. And doing the algebra, we get this matrix over here. And from this matrix, we can decompose it into the weighted sum of these Pauli matrices, and we get that R corresponds to vector over here, which is exactly the same vector we got when working in the pure state formalism. So our final topic is going to be the reduced density operator. So we've dealt with density operators for a single qubit, but what about density operators that encompass two different systems that are coupled together, bitart systems or tripartite systems? And how do we extract the density operator of one subsystem from the density operator of a total subsystem? Well, in this case, for mixed states for systems comprised of many different subsystems, we can use the density operator as a descriptive tool for subsystems of a composite quantum system. And such a description is provided by what's called the reduced density operator, defined as the partial trace with respect to the opposite system. So what is the partial trace? Well, the partial trace is mathematically defined as this operator, in which instead with the regular trace, we simply took the expectation value of each of the basis vectors. Instead, we're taking the expectation value with respect to one subsystem, in this case B, and we simply take the identity for the other system. And this is defined as a partial trace. And so, for example, let's take this Bell state over here. And for the Bell state, it's a pure state, so we can calculate the total density matrix as follows. Now, we are going to calculate the subsystem density matrix for A using the partial trace with respect to B. And so this can be done by taking the trace, of course, this operator over here. We're going to take the trace for only the B system over here. And we repeat this for each of these entries over here. And of course, we know the trace for each of these as follows. And so we simply multiply each of these entries by these values, and we can see these cancel out to get this value over here, and we get the half of the identity, which means that this is what's called a fully mixed state, which means that we don't have any information on what it's totally maximally. Basically, we don't have any, it's a state of maximal uncertainty, basically. So it can be in any of the two outcomes with equal probability. So why do we use the partial trace to extract the density operators of subsystems? Well, suppose we have an M, which is an observable on any system, and that M tilde denotes the corresponding observable for the exact same measurement, which was performed on the composite system AB. And M tilde is necessarily equal to M cross the identity, because physical consistency requires, let's say, consistency requires that the expectation value of M and the expectation value of M tilde with respect to the composite system and the subsystem respectively be equal to each other. So if this is the case, we simply let's take the trace on each of these sides, and we get this final expression over here according to the definition of M tilde. Well, going through the algebra, we can see that we take the trace of this expression over here, and then if we go down to the line below it, of course, the tensor product is also a linear operator, so we can do this as so. And then we also expand to include the identity of B over here, and we basically slide this expression in between these two expressions. And then since we can use the commutative property of the trace to rearrange these terms over here, and you'll notice that this expression over here is the definition of the partial trace. And so we've derived the subsystem density operator as defined by the partial trace by basically assuming that the corresponding measurement on a composite system AB is simply the measurement on the observable A and the identity on the subsystem B. So that's all for this lecture. I'll see you in the next one.